Hello, everyone. Thank you for joining us today. My name is Marc Richardson, and I'm with the Civic Data and Technology Clinic at the University of Chicago. Today, my teammates and I are going to discuss the work that we did with Hohonu to further its mission of assisting communities that are harmed by frequent flooding. In this video, we will discuss some of the challenges that we addressed during the project. First, a brief overview of our partner organization. Hahonu provides technology solutions that enable real-time measurement and prediction of water levels at locations around the globe. Hahonu's work is critical for coastal stakeholders as it allows communities to detect and prepare for devastating floods before they happen. Hahonu accomplishes this by manufacturing low-cost solar-powered smart nodes that produce real-time streams of data which enable real-time analytics. We worked with Hahonu to provide data-driven insights into challenging obstacles that it currently faces. The first challenge we faced was identifying anomalous or outlier data points. This analysis is absolutely critical for two reasons. First, system anomalies, or data that is inaccurate and biased, can signal that a sensor is malfunctioning, which indicates the presence of bad data. Bad data is like kryptonite to a predictive model. It interferes with accurate forecasting. Therefore, removing such data before feeding it into the model can improve performance drastically. And second, anomalous data can also occur as a result of natural events, such as storms and abnormal tides. Detecting these natural anomalies is essential for mitigating the harm from extreme weather events. A large part of our project involved gaining a better understanding of both these types of anomalies. The second challenge we faced was figuring out how to effectively communicate anomalies to the appropriate stakeholders. We sought to use data visualization and a dashboard application that stakeholders could use to stay informed. The third challenge we faced was to improve Hohonu's real-time prediction model in terms of efficiency and accuracy. Anomaly detection is a big part of that, but we also sought to explore alternative state-of-the-art algorithms that would perform as well as, if not better, than Hohonu's current model. This required careful testing and comparison between model performance. And finally, our fourth challenge was optimizing Hohonu's data pipeline. A lean data pipeline is essential to real-time forecasting. We sought to increase the capacity of Hohonu's pipeline through the utilization of distributed storage and cloud computing. Before getting into the details of how we address these issues, let me first give a brief overview of the tech stack for this project. Our language of choice is Python. We use Docker containers to deploy the dashboard application, and Django provides the framework for that application. Currently, Hahonu uses Amazon's object storage S3, but we've been transitioning Hohonu's data storage over to a Postgres database that resides on Amazon servers. And finally, Hohonu's sensors use particle hardware to access the cellular network for data transfer to the cloud.
Our first problem is detect anomalies, so our users can be aware of potential problems such as storm or hardware error, and also removing anomalies from our data can help us make more accurate predictions for our user. Basically, we did anomaly detecting for two variables, water level and voltage. For water level, we use the Quartet standard. Quartet is a quality assurance or quality control of real-time oceanographic data, and it's a standard way to quality control for water level data, and is also adopted by NOAA. Basically, we did 4 tests for water level. They are the gross rain test, flyline test, stack test, and rate of change test. We also use map value according to the anomaly boundaries. So as you can see here, 5% will be mapped to 25%. This way can help us detect anomalies faster. We visualize our result of the change of anomaly rate compared to yesterday. As you can see in this plot, 2 lines here are the anomaly rate for each node each day, and bar plots here are the change of anomaly rate compared to yesterday. As you can see here, when the anomaly rate begin to increase, map value can help us detect anomaly rates faster, so our use can be warned earlier.
Okay, so after Cartod, we now know it's important to measure for anomalies in water levels. But for Hohonu, it's also important to measure anomalies in the voltage levels of the batteries that power their sensors. Monitoring voltage anomalies can help Hohonu prevent batteries from going offline, which is a critical business need, because voltage levels give us a glimpse into the moment-to-moment health of the hardware. Unfortunately, there's no developed framework that would be the voltage equivalent to Cartod anomaly detection, which meant develop our own. Developing that framework was a huge challenge for us. We needed to figure out what events might cause anomalies, So deciding what to measure and how to measure it was where we spent the majority of our time on this problem. We brainstormed events that could lead to unusual voltage levels, like frayed wires or a storm, and chose measurements where such behavior would be captured by proxy. I'll briefly touch on two of those measurements, peak-to-peak slope and charge gain, in just a moment. So we know it's critical that Hahonu knows about unusual hardware activity in real time, because Hahonu has nodes all over the world and those nodes need to be reliable. With that in mind, let's look at an example using two of our measurements from a node on the Massachusetts coast. So here we have voltage levels for the first 2 weeks of November, along with two of our anomalies, peak-to-peak slope, which tells us if our node is charged unusually more or less than yesterday, and charge gain from sun, which measured how much sunlight a node was exposed to. This precipitous drop in voltage levels is a 2-day-long storm, and you can see that anomalies are clustered around this major storm, and that's a positive sign for our work. We expect future iterations will build on our work and establish actionable patterns of anomalies.
Now, our next step is how do we visualize our anomalies? And let me introduce this. Now we want to get our anomalies on our web page, so we add a new tab here called anomalies besides our sensor dashboard. And this dashboard is also a list of our nodes. And these nodes, we created a card view besides node list tab to show the anomaly of each sensor by different methods. And within each method, sensors are sorted by the mapped value of our anomaly, with larger number comes first. And we know that this is updated simultaneously. So when something happens, our administrator or engineer can directly read the anomaly on a single page and know which nodes should be taken care of. And for each node, we added a anomaly rolling change plot, and this is a time series representation of the anomaly by sensor. And with this plot, our engineer can track the anomaly for the past 2 months. And this can be an essential complement to the prediction plot besides the rolling change plot. So these are what we got for our main web page.
The next problem is detecting coastal flooding using machine learning algorithms. Every year, flooding causes massive damage to coastal cities. To prevent the disaster, the first step is predicting it and sending out early warnings. Currently, both Hohonu and NOAA are putting efforts in the prediction, but the accuracy is still not ideal. Our task in this part is researching other machine learning models to improve the accuracy. And in particular, we'd like to see whether our new model can outperform both the old one and NOAA's model. Currently, Hohonu uses VAR model, which performs well but has a high latency and does not handle missing data very well. Therefore, we sought to find another algorithm that can perform as well as VAR but with lower latency and greater reliability. We explored 2 different models, the Prophet developed by Facebook and Tspdb that works on top of PostgreSQL database. This figure is an overall of our result. The purple line representing Prophet model, and there is a black line below the purple line representing Prophet model with a seasonality parameter. The Prophet's RMSE is high, but it performs rather stable, as indicated by the very narrow confidence interval. VAR model, on the other hand, has low RMSE for 1-day prediction, but fluctuates a lot for longer period. The result is more obvious in those figures. Using same 1 month and 3 months dataset, VAR model outperforms Prophet in 1 day, but Prophet has better stability and is less sensitive to anomalies. And this is another perspective. Predicting for a same length of period, Prophet has less fluctuation. So to conclude this part, for short-term prediction, VAR is still our best choice, and it also outperforms NOAA's model. But if in future, Hohonu wants to extend the prediction to longer than 7 days, Prophet can be a better solution.
We also explored using another algorithm called Tspdb, which is implemented directly into a database and can support lightning-fast real-time forecasting. However, we found that the model performs sporadically. On some days, the model produced reasonable forecasts. On others, its predictions significantly deviated from the test data. Nonetheless, we encourage future project teams to build on our initial exploration, as Tspdb's low latency forecasting and ability to impute missing values could dramatically improve the runtime of Hohonu's forecasting analytics.
The last project we worked on was to begin the process of migrating Hohonu's data pipeline to AWS. Currently, a significant amount of data processing is done using the standard data manipulation libraries in Python, which presents reliability problems because they introduce the potential for human errors in coding. Additionally, data is retrieved via multiple APIs, which is time inefficient and introduces problems with consistency. So we added a database in AWS, created simple tables for future iterations to build from, and wrote some code to talk to the database that would allow us to insert and retrieve data. Additionally, we were able to move some data processing to the database, which provides significant speed benefits, reliability, and consistency. While simply standing up the database provided real benefit to Hohonu, there is still plenty of work to be done, and we expect future work will focus on further developing the schema.
In conclusion, here's what we accomplished for Hohonu this quarter. We added dynamic functionality for detecting anomalies in water level and voltage data. For the dashboard, we added new anomaly detection visualizations to communicate when nodes are malfunctioning. On the machine learning front, we researched other algorithms to improve prediction without sacrificing accuracy. And finally, we started to build out a new data pipeline using AWS tools to increase efficiency and stability. We believe that future project teams should focus on the following: continuing to refine the anomaly detection and test the accuracy of the analysis, further exploring alternative real-time prediction models, including tuning of hyperparameters for models that we already tested. On the dashboard front, redesigning the dashboard application to include views that more effectively communicate a node's existing predictions and anomalies. And finally, further optimizing the database architecture for fast data retrieval, as well as shifting the existing pipeline over to the cloud pipeline. So thank you very much to both Hahonu and the 11th Hour Project for funding, and a big thank you to our instructors David and Daniel for their amazing and tremendous support and advice through this quarter.